Today we have with us Melanie Herrmann, who is currently doing her postdoc at Cambridge University and closely collaborating with company Visuality. She holds a PhD in human-computer interaction from University College London, and she will tell us how in her company and in her research they are using psychology and human-computer interaction to visualize different type of data, especially for sustainability purposes. Welcome, Melanie.
Thank you. I should say that the program I'm on is called the Knowledge Transfer Partnership, which is funded by Innovate UK. So the entire idea is to get academics and industry to work together more closely and to apply research and science in the product. So first of all, I'd like to tell you a bit more about Visuality so that you can get an idea about who they are and what they do. They are a data design company and they work together with other big organizations, Google, the United Nations, the World Resources Institute, and essentially they make platforms that all have to do in one way or another with the environment and biodiversity. So I brought you a few examples. That one is Climate Watch, and in the example screenshot you can see global emissions for different countries and their development over time. So this is an open data platform that is basically made for governments, for stakeholders to track the progress that individual countries make in the fight against climate change. This is another one that Visuality has made in the past. It's called Global Fishing Watch, and it provides you with near real-time information on what commercial fishing vessels are doing. So what you can see is the white dots. Every white dot is a fishing vessel. And based on their GPS signal, you can track their movements and see what they're doing, where they're going. And then on the map, you can select different layers. So for example, you can see exclusive economic zones, or you can see areas that are protected by law. So fishing vessels are technically not allowed to enter and to fish there, but if they do, you can use that data to create just more transparency and to create accountability for fishing vessels. Global Forest Watch is one that shows gains and loss of forest around the world. This is based on satellite data, and I'm not sure if you can read that, but you can see the different drivers of forest loss. So some of it might be commodity driven, some of it might just be wildfires, some of it might be urbanization, and you can look at all these different drivers separately and you can analyze where forest is lost. So to maybe give you a nice success story from this one, there was a case where a local NGO used this and they were monitoring a certain area in their region and saw that there was suddenly a lot of deforestation going on and there was no explanation, they didn't know why. And they sent somebody to investigate, and it was actually the case that a company went in there, chopped down forest to use it to grow cocoa, and they actually had their license taken away based on the data that the NGO used to track them down. So that was a success story we had with Global Forest Watch. Trace is related to deforestation as well. So you might be aware that a lot of trading companies have committed to reducing the deforestation associated with certain commodities. Soy, palm oil are the ones that you've probably heard of before. There are big problems with that, and Trace is creating this transparency of the supply chain. So it monitors, in this example, soy from Brazil, and you can see from every single municipality where it goes, which company is buying it, who they're selling it to, and then what you can't see, because I had to chop it off, it didn't all fit in one screen, is the countries it goes to, but you see the color coding of the lines and the Sankey diagram, and you see at the bottom the countries. So you can track exactly where everything is going, and you might want to use that in your decision making, who to trade with or which region to avoid, because it's already been suffering too much from deforestation. And just a last one, because it's a little bit different, Half Earth is based on a book you might have heard of. It's basically the idea that if we can create half of the land and half of the oceans on our planet, we can do fairly well in protecting most of the species that we still have at this stage, and to just make sure that we preserve the most important habitats and reverse the disappearance of species that we've already been seeing over the last decades. In this example, you can see turtles, and it basically shows you for different groups where species are, where their highest density is. So this is again data that is used by governments, by NGOs to identify the areas that most need protection. So much as a small introduction to Visuality. They have loads of other projects they've worked on over the past years. If you want to have a look on the website, feel free. If you have any questions, do come back to me and we can have a chat about it. Now, I am a psychologist by background. I'm guessing that most people in the room have a technical background. Why would a tech company want a psychologist on the team? I brought you an example. That is my favorite example from my ergonomics class in my undergrad. And this might seem like a rather innocuous design question. So imagine you work in the automotive industry, you're designing a cockpit in a car, and you have to pick the illumination for the cockpit when people drive at night. Show of hands, who's going for red and who's going for red, first of all? Who goes for blue? 2 people over there. 1, 2, 3, okay. More people want blue than red. Now, there are actually a lot of psychologists working in the automotive industry in research and development, because this is not just an innocuous design question. This is actually a question for neuroscience and for human factors. So if you had anything on the visual system in biology in school, you might remember we have different cells in our retina, and different cells process different kinds of information. And roughly speaking, there are 2 categories. There are rods and cones. Cones allow you to see red as red and blue as blue. They deal with color. And the rods don't have to do with color, but they are the ones that enable you to see under different conditions in terms of light. So if you get up in the middle of the night and you want to grab a glass of water, you don't want to switch the light on, right? Because you're really dark adapted. The sensitivity of those cells is high up. So even under very low light conditions, you're able to see. And of course, when you drive a car in the middle of the night, that's really important. You want to be adapted to the dark. You want the sensitivity of those cells really high. So if you look out on the road, you want to see everything that's happening. If you look back into the cockpit and onto this display, then blue is not the best choice you can make, because the sensitivity spectrum of these cells overlaps with the sensitivity spectrum of the blue cones, meaning if your light sensitive cells look at this, they will lose some of their adaptation. They will respond to this light. This light is roughly 450 nanometers, and that falls within the sensitivity spectrum. So you will lose some of that adaptation. You look back out onto the street and you're blinded by the blue light, which is not what you want. Red, on the other hand, is 700 nanometers, has a different wavelength. Only the red cones will respond to that. The rods have no reaction to that whatsoever. So this is actually a question for neuroscience and human factors. Psychology in general is the study of mind and behavior, and that includes conscious, subconscious processes, thoughts, feelings, and the basis for a lot of the work in psychology actually comes from biology, from physics, from neuroscience, from brain imaging studies. And that immediately informs human factors, human-computer interaction, and usability UX. I'd like to talk about the visual system a bit more, because it's a really impressive one. You might know that most of our body and brain are contralateral, so the right half of the brain controls the left half of the body and the other way around. The visual system is quite different from that. It has fibers that cross over, like most systems do, but half of the fibers actually stay in the same half. And the visual path is a really long and really complex one. There's a lot of steps happening even before the information gets to your primary visual cortex, which is all the way through the brain at the very back of your head. And from there are different streams that go up and down. And they're very, very, very specific areas in your brain that process specific characteristics of images that are coming in. So why is it so complex? It is simply a product of evolution. We have evolved to see landscapes, for example, natural images, because our brain and our entire sensory system is made so that we can navigate through everyday life, we can interact with other people, we can be safe. So we're really good at this. This is pleasant to look at and easy and automatic to process. I said there are specific areas that process very specific aspects. We have a separate area in the brain that's responsible for faces, and that's why we're so good at it. Landscapes, faces, these things, it takes us a split second to understand what we look at, even under really unusual conditions. So in this case, the face is covered, there are hands covering half of it, it is covered in color. This is not how we normally see faces, but because we're so good at it, because our brain is so trained in doing that, we can do it in a split second. Makes a lot of sense, of course. We're social beings, social animals, so if we see a happy face, if we see somebody smile, that actually makes us happy. It's something we quite like and we have a strong emotional response to. On the other end of the spectrum, if somebody has a very angry expression on their faces, we might choose to run or fight, or in a slightly dangerous scenario, it might just determine if you offer your partner a cup of coffee in the morning before you try to talk to them, right? So it's just something we can do automatically. It's really easy. These are the things we're good at. This is what the visual system is built for, or what it has evolved to do. And I think it's just worth noting how good we are at that. A few years ago, I worked for a UX agency for a while, and we were testing out face recognition software that was meant to detect emotional responses in people's faces. And it was not very good at it. So even with computers, and we can do a lot these days, but there are things where we're still better as human beings just doing it automatically than trying to give that task to a computer. Now, the things we're not good at is anything artificial, basically. You've seen all sorts of visual illusions before in your life. In the upper example, we tend to think that the inner circles have a different size when actually they're exactly the same. The vertical lines over there have exactly the same length, but the arrow endings distract us, and we seem to think that the right one is shorter. And at the bottom one, all the grey lines are parallel, and yet our brain wants to make us believe that they're slightly bent. You don't need to look at the details of this. Some of you might have seen that before. This is a very famous paper from the 80s on elementary perceptual tasks. So this is all the bits that inform graph theory and the science behind what graphs we're good at and which ones we're not so good at. So if we compare lengths of lines and the lines start in the same origin, that's very easy for us. This is why bar charts are a very easy chart for people to analyze. On the other hand, we're not so good at estimating areas or angles, and therefore lots of people do not like pie charts. This is pretty much what we can do, what we can't do, what we can do easily or not so easily. There's a next level of that goes as far as causing discomfort or even visual stress, as it's referred to in psychology. That is an image that I don't like to look at for very long. I can, though. There are very vulnerable populations for whom this might go as far as triggering headaches, migraines, or even seizures. We probably have physicists in the room. You might be familiar with Fourier analysis, so this just comes down to the spatial frequency in the image. And the distribution of spatial frequencies in this image is just very, very far away from what we would find in natural images, from faces, landscapes. Simple as that, brain is not made to process it, and therefore is very unpleasant for us to look at. Now, how does all of this relate to data viz and the company I'm with? I spent a few months looking at environmental data viz websites, just seeing what's out there on the internet, and I saw a lot of good things, and I saw lots of things that, from the cognitive and psychology perspective, were a bit challenging. This is Fix My Street, that's by My Society, and personally I really love it. It's very fun to play around in there. You can report and discuss local issues. So the big note that I was looking at the time was a fun story of a woman who was complaining about another woman who was feeding hundreds of pigeons who were, in her words, fouling the street and holding up traffic. So it's quite nice from the kind of citizen science perspective, from the community perspective. You can go to your local area, you can share, you can submit potholes. From the visual perspective, I think this is not one of the prettier ones I've seen. You see the high density of the fine black lines to show all the houses and all the streets. So from the spatial frequency perspective, this is just not very pleasant to look at for a very long time. It's not really made for it. Another point that I'd like to transition to now is how much of that can we actually see at any given time. So you can choose. You can hold a finger out in front of your face, focus on your finger, and notice how everything around it is slightly blurry. Or if you feel stupid doing that, you can look at Finsbury Park in the middle. I hope you can read that from where you're sitting. But if you focus the word Finsbury Park, you won't be able to read any of the other words. And that's because we have a very small spot in the retina called the fovea that allows us to see with high resolution. And that is just about 2 degrees of your visual angle. So you're quite far away now, but say you're working on your computer, you're normally 50, 60 centimeters away from your computer screen. That means the area you can see on any given screen is around 2 square centimeters, which is very small. if you think about the screen sizes we have nowadays, that's a tiny area you can focus on at any given time. So all the information on that screen, all the data we have, all the parts and details of an image we can show to people, they will only ever be able to see a very small part. So there is a major physiological restriction on how much people can take in and process at a given time. Now that's the physiological restriction. There are others in the cognitive system. So visual attention and short-term memory both have very limited capacity. We like to think we're quite good with a visual system, but I brought you a couple of really simple examples that show that we're not. This is a classic experiment from basic psychology, feature search versus conjunction search. If I ask you to find the green tea in here, you do it immediately because your visual attention is automatically attuned to the green. You're told you want to look for green, there it is. And if it's just that one, it is absolutely not important how many distractors there are because you automatically go to the green one. If you were to measure that in an experiment in a lab, you could see response time going up just by the fact that we add something else that has a relevant feature. So here you need to analyze two features. So that's what we call a conjunction search. You have to scan for shape and for color. So it takes you longer to find the T. And that time will go up and up and up and up the more distractors I add. So this is a really simple example. This is nowhere near the complexity of modern data visualizations, and yet we're already significantly reduced in our response time if there are other things, just because our visual attention is very limited. Short-term memory, similar one. It's a very simple grid of 12 letters. It's not a complicated thing, but if I take the slide away in a second, it's rather unlikely that the majority of you will be able to memorize and recall all 12 of them correctly. It's that idea of the bottleneck, that we can only take in so much at a time, retain it in our memory, and then recall it. So if we look at the application of all that, then there are limits on what the average human mind can do with complex data visualizations. I've seen a lot of things online that are rather cluttered. So if we take this one, for example, there are a lot of elements. If I remember that I can only see 2 square centimeters at a time, that means I have to move around in this a lot. Now, the visual system has a lot of quirks. Your eyes can't move very smoothly. If you ever observe somebody when they're reading, you will notice that the eyes can't move very smoothly letter by letter. Rather, they do little jumps. And while we do these jumps, we're technically blind. We're actually not having an image. It's just the brain that's doing a lot of computations that fills in the gaps, because frankly it would be quite scary if we just had all these little blackouts in between. But it is effort, and we have to move around, and it's not very accurate. This is the reason why a lot of journals and magazines choose to have a layout with 2 small columns, because we're not very precise in these jumps. So if you've reached the end of one line, jumping back to the beginning of the next line is easier and more precise if we have a short distance to cover, rather than if we use the full width of a page. So in this one, on top of everything else, the legend on the side, the color coding, is not very distinct. So we have to make loads of these little jumps, going back from the map to the legend, trying to figure out what color is what, and have to memorize that. And it's just not very much in line with how the human mind works and how our cognitive system is designed. The last concept I'd like to talk about is mental models. And I'm going to show you an example from my PhD. Which was on smart metering and household energy use. And it's quite an interesting one. So we had a brief chat about this before, just 10 minutes ago. A mental model is just your idea of something in reality. So if you imagine a dog right now, you know what it looks like. So you have a thing in the real world, and you have a mental representation of that. And then we can create external representations. We can build an architectural model of a real building, or we can produce a piece of data viz. So that's an external representation that, in the best case, helps us to think about it and helps us improve our cognitive processes and to understand it better. But there can be mismatches between our mental model and the external representation, and the more they mismatch, the more they clash, the more difficult it becomes. So in the case of smart metering, if you have one, you probably have been given an in-home display. And they have very simple visualizations. They typically come in either dials or sort of speedometers, or in these bar charts that show you in green, amber, red how much energy you're using. And that's rather basic. If you look at commercial systems, where you can log in online, create an account, and see your entire energy history and your recordings, then you can typically get a bit more information, because you can see your history day by day. You can see when your peaks were, how much energy you used at what time. And it's quite interesting, because if you go through tools that householders can use as a piece of energy feedback, if you go through academic publications, then you will find that the majority of energy visualizations are time series line graphs. And that makes a lot of sense from the data, right? So this is somebody who did his entire PhD on collecting household energy data. And this is from one of his papers. And that shows the data as it is, right? Because what you have is a timestamp and a power reading. So it seems very intuitive to show exactly that, power over time. And it's interesting, because even if you talk to people who are not scientists, who are not in the energy business, they will do exactly that. This is a study I ran with householders, and I asked them, could you sketch what you think your energy consumption in your home looks like over a day? And every single one of them did just that. They drew a coordinate system, and they showed power fluctuations over time. Now the interesting bit is that in the very same study, where they received online feedback in form of a time graph, and in other studies I did afterwards, I found that people don't learn very much from it. The best case scenario is that they find out what time roughly their peak time consumption is. But then again, there's something that most of them knew before, so they don't really learn any insights about their everyday life, or ideally how to be more sustainable, how to save energy, how to save money. So this is where social science and social practice theory comes in. And this is what I mean with a mismatch between external representations and mental models. Because most people in their home think about energy as making a cup of coffee, running the dishwasher, washing my laundry, and I don't really know watts or how many watts I'm using for which activity. And this entire idea of power fluctuations over time, it's really interesting if you're into data. I was quite intrigued to find out that you can identify the pattern of your washing machine if you spend a bit of time looking at it, but it's just not how people think about it. So what we found is that if you change the perspective and you give them the data in a way that's more in line with how they think about it, they can deal with it in a much better way. They're much more interested, and they say, oh yeah, this is obvious. So this is simply a pictographic feedback format where the size of the icon in the household is just scaled up to the amount of energy it has consumed over a certain time period. And this is what we found in thematic analysis of the interview data, that people would make much more connections to their everyday life, that they would analyze a lot more how they were using energy, that they would say, oh my god, my flatmate is watching way too much TV, we should talk about that. He keeps it on and it just falls asleep and keeps it running through the night. So this is an example where we found that mental models had a big influence of how a user could extract information from data viz. Now this was my PhD. Now I'm with Visuality. What are my research questions right now? In general, our big dream is that we could figure out some set of guidelines, a science of data viz, how to build data viz in a way that is successful and impactful. So can we come to the conclusion, if we have data set X for topic Y, can we come up with guidelines and recommendations, what you should do with that data set to show it to people, to make it impactful? One of the aspects we consider is visual stress and visual clutter. So this is where the psychology bit comes in. The images I showed you that are stressful or causing visual discomfort. And the assumption is that consciously or subconsciously, if you show people very unpleasant stimuli, they will not spend as much time using the website. So if you show them a map that has a very unpleasant base map with a high density of grid lines, it will just not be a pleasurable experience to use that. And ideally, we'd want to build tools that are showing all the data we have, but show it in a way that is pleasing, that is engaging to people. So related to the first point, we'd really like to find out how to make visualizations good and align with human cognition, but also to design them in a way that people have fun looking at them, that they find them engaging or even immersive, particularly if you think about maps and the use of 3D. So most of the data we work with is geodata in one way or another. Some of it might be satellite data, others might be based on crowdsourcing and citizen science, but it's all about where are the trees, where are we losing trees, where are we planting trees, where are certain species located, which are the areas we need to protect. So if you think about a globe, if you have one at home, have a look at it and compare it with a map. Depending on the projections you choose, going from the Earth as it is, the real thing, or also your mental model, hopefully in all our heads it's a globe, to a map, that is a representation that's not very accurate. And there are certain distortions that are going to happen. So some countries on a map look bigger than they really are, and others look smaller. And this is a really interesting research question for cognitive science and decision making, because people will necessarily over or underestimate the size of certain countries because they are wrongly represented. So it's actually not accurate what we show on maps. And as far as I'm aware, there is not a lot of research on that. So if we also tie in the emotional aspect and how do we get people on board, how do we make it nice to look at, engaging to interact with, then it might be that globes that you can zoom in and turn around and play around with might be the better solution to engage people. There's a lot of development going on at the moment with 3D, which again I find really interesting, because if you go back to theory and graph theory, 3D is something that is mostly discouraged. Graph theory is very pragmatic. It always tells us to keep things simple, right? And to just show what's necessary and not add too much. And then there are more modern papers coming in that actually we can increase memorability if we add objects, if we add shapes that are meaningful to people, such as shapes of animals or maybe environmental things, faces, humans. And 3D is something, I'm going to show you an image in a second, where I think particularly for maps, this is something where we can add a lot of visual depth to things that we haven't seen so much in the past. And another research question related to maps is how do we show change over time? So if it's deforestation, if it's the loss of biodiversity, we're interested in how does it develop. We don't just want to know the status quo, we want to see does it go up, does it go down, what is happening. So we're talking about things that change over time, and it might also change over geographies. So if we look at a few examples, this is from the movie Chasing Coral. I don't know if you've seen that one, but it's quite emotional really. At the end they show these comparisons of before and after pictures they've taken from coral reefs. And I think this is really powerful emotionally because people see that drastic contrast. However, if you want to show change over time for complex data sets, this is sort of aiming for a similar before-after comparison solution. And as a cognitive scientist, I have to say I'm not fond of it. So what you have here is you have two sliders. The bottom one allows you to move through time. So this is where you can see the change over time. And then you have an additional one that allows you to simulate different scenarios. So one is low emissions, the other one's high emissions, and you can simulate different scenarios. But if you go back to what we said about limited short-term memory and limited visual attention and how much we can actually see, then this is mind-boggling to me, because I don't think it's possible that personally I can look at this, memorize exactly what the heat map looks like, memorize which pixels are dark red, which pixels are yellow, and then move the slider, thus losing what I just looked at, and then seeing a different scenario and in my mind trying to recall what I just saw and compare it in my mind and try to figure out what the differences are. So I think for the average human being, this is just too much. It's beautiful. I think it looks nice from a design perspective. I see why you would go down this road. As much as I understand that some people might just prefer a blue illumination in their car cockpit, but as a cognitive psychologist, I would not advise doing this because I think it is too much and the average person will miss out on details. It is not possible that you will see all the changes that are happening. If you just think about everyday examples, we all know these pictures in magazines where they say, spot the 5 mistakes. And we go back and forth, and this is under a condition where we see both of them at the same time. And here we simply can't do that. We lose one if we look at the other. Global Forest Watch is one that I find super interesting from the perspective of mental models. Because the way I think about forest and forest loss is I have forest, and when I lose it, it's gone. And the mapping here, the relationship is negative. If I lose forest, it will be displayed as a pink pixel. So pink is tree cover loss and blue is tree cover gain. And that adds another layer of complexity, because in my mind, I would kind of have to do the math and find the difference, see, oh, this is how much was lost, but this is how much was gained. So actually, it's still forest gained, and this is not shown. At the same time, I do have to say that it really depends what you're looking for. Because if you want to focus, say, on tree cover loss, if you want to keep an eye on where deforestation is happening and maybe check that there's nothing illegal going on, then the pink is a very visually salient color. So in terms of directing your attention, if we remember we can only see a small area, our visual attention is very limited, then it's in terms of signal detection, it's a very powerful solution to drawing people's visual attention to the bits where something is happening. So if suddenly a lot of pink pixels pop up in an area, we're very likely to just automatically go there because our eye will register that something is going on and will pop to that region. And the last one, because I touched on maps and 3D, is this one. What it shows is road accidents in the UK, obviously London being the epicenter. And I think this one is really cool. So first of all, as a cognitive scientist, I have to say it's amazing because it's one of the few examples I see where people respect the rule that you should always double code information. So there's the height of the bar that shows how many accidents have happened, and in addition to that there's color coding. A lot of data viz relies on color coding only, and that is fine for most of us because we're lucky enough to be able to see that. There are, however, up to 8%, I think, of male people in the population who suffer from red-green blindness or other color impairments. So for most of the websites I've seen, if your color vision is impaired or you suffer from red-green blindness, there's just no way you can use them. You won't be able to extract the information. So this is a really beautiful solution that's accessible even if you are impaired in your color vision, where you can rely either on the color or on the height of the chart or both, and you can extract the information. And I think it just looks pretty cool. I like the fact that the map is combined with that 3D effect. And I think if we were able to create more data viz like that has that kind of coolness factor to it, it might increase people's engagement. And this is something we're really interested in as well. How can we measure people's response, and how can we make data viz in a way that draws people in and makes them think this is actually cool, data is interesting, we want to engage with that and we want to be part of that. So as a closing thought, I wanted to share that quote, which says that the conclusions people can draw from their analytical efforts are always restricted by the form in which they receive data and by their limited analytical capabilities. This is from a paper on energy data in particular, so the bit I cut out there, the 3 dots, is price and consumption data, but it really applies to any scenario where you have people trying to analyze data. The format in which we present data and people's natural ability to analyze it will always impact how successful our data visualization will be. No matter how cool the underlying data set, no matter how good the data science that we've done to it, if we present it in a format that bends people's minds and just doesn't respect human cognition or the visual system and its properties, it will be really hard for people to engage with it. It will impact the user experience they have with it, and ultimately it will limit the success we have with data viz and showing these things. That's the end. I think we have time, but if you want to follow up with me later or questions come up later on, please feel free to send me an email or ping me on Twitter. We do blog about our work on Medium as well, so if you're interested, that's where you can follow me. Thank you.